Hi everyone. My name is Jill Cates, and I'm a data scientist at a company called BioSymetrics here in Toronto. So earlier this year, I was tasked with the challenge of building a deployable recommender system for medical research papers. I quickly learned that there were many resources out there for recommender models, but finding information on all of the other steps involved for a recommender pipeline was extremely difficult. So today, I will be walking through all of the steps involved for building a recommender pipeline. So I'll be going through the steps of pre-processing, hyperparameter tuning, model training, post-processing, as well as evaluation. So by the end of this talk, you'll have a good idea about where to start and what tools to use to build a recommender pipeline of your own. But before we get into the details of this pipeline, I'm first going to give you a quick intro about recommenders. So as many of you probably already know, recommenders are everywhere. We see it in Spotify with Discover Weekly, where they generate personalized playlists. We see it in Netflix. So because you watched Orange is the New Black, we recommend you watch all these other shows. We also see it in Amazon. So customers who bought this book also bought all of these other items. We see it in dating sites. So they typically gather all of this information about you and try to guess who the best match would be for you based on your personality. And just to continue with this list, job searches, the news, and even in medicine for clinical decision making. Recommenders, though, are a very hot topic in e-commerce. But back in the day when e-commerce didn't exist, things were sold exclusively in brick and mortar stores. So a store's inventory was limited to the space of the store, and products that didn't sell well weren't profitable. So the most logical choice was to only sell the most mainstream popular products. And I'm sure most of you have walked into a bookstore and have seen straight away all of the bestsellers presented to you. But once e-commerce came along, this changed the way that we sell things. So we now have an unlimited inventory, which means that niche products that were previously neglected in brick and mortar stores are now easily accessible online. And so for those of you that have read the book called The Long Tail by Chris Anderson, you'll learn that niche products generate a surprisingly huge amount of revenue in online retail. But having a massive selection of offerings doesn't necessarily mean that users will buy more stuff. So in the year 2000, there was a research study conducted at a supermarket tasting booth. One booth had 6 samples of jam, and the other booth had 24 samples of jam. So the booth with more samples attracted more users, but it turns out that the booth with 6 samples had a 30% conversion rate, and the booth with 24 samples only had a 3% conversion rate. So having a wide variety of options may seem very appealing to consumers, but it's been shown that it actually reduces their motivation to later on buy a product. And one possibility is that they're just so overwhelmed with all the options. So this is where recommenders come in. It's very important that when we have unlimited inventory, that recommenders filter out only the most relevant items for a particular user. Okay, so a recommender system is just like any machine learning model. You start with some data, you pass it into the model, and it outputs predictions. So in this scenario, our data is a user's preference towards a product. So this can either be in the form of explicit feedback, so a user giving direct ratings or directly liking a movie, for example. And it also comes in the form of implicit feedback. So this is a little more subtle, but it's your indirect behavior towards an item. So whether you binge watched that show or you clicked replay for a song, so on and so forth. So by feeding all of these user preferences into our recommender system model, we are then able to generate predictions on what your future behavior will be like. So we're predicting which song will you love next, or which show will you binge watch next. And these are essentially what we call recommendations. So there are two common approaches to recommender systems. We have collaborative filtering and content-based filtering. So collaborative filtering is based on the premise that similar people like similar things. So let's say we're building a movie recommender. It doesn't know who you are or what these movies are. We only look at the interactions that you have with these movies and other users' interactions with the movie. So the core data of a collaborative filtering model is the user item matrix, or what we call the utility matrix. And so each number in this matrix represents a user's rating of a given movie. And our goal here is to fill in the blanks of this matrix. So essentially we're trying to predict what you would rate all of the other movies you haven't watched yet. Okay, so the other type of recommender is a content-based filtering model. And so this looks at the content of users and movies. It takes into consideration your traits, such as your age or gender, what language you speak, and it also looks at traits of the movie. So the year it was produced, whether it was scary, funny, an indie film production, or a major film production, and looking at all of these features, it tries to generate recommendations that way. So now that we have a better idea of what a recommender is, let's start with building our pipeline. So I'll be walking through all of the 5 steps of this pipeline, which include pre-processing, hyperparameter tuning, model training, post-processing, and last but not least, evaluation. So to continue with the movie example, we're going to be working with the data set that provides us with users' ratings of movies. So we don't know anything about these users, we don't know anything about these movies, we just have the ratings. So this means we're going to be using collaborative filtering. We first need to transform this table we have here into a user by item matrix. And in this matrix, each row represents a user's ratings, and each column represents the ratings of a movie. And so all of the cells here are populated with the ratings that we were given. So this matrix is typically represented as a SciPy sparse CSR matrix. And I just want to note that all of these empty cells here, they're not filled with zeros, they're actually empty. So even though your matrix could be very big, it's typically a small in size. And so that's actually a drawback that comes with collaborative filtering. It doesn't perform well if your data set is sparse. So it's important for us to calculate the sparsity of our matrix. We can do this by counting the total number of ratings that we have and dividing it by the number of cells in our matrix. And if our data is too sparse, so something like 0.5%, then collaborative filtering might not be the best option. It's also worth considering looking at how many new users and new items we have. So if you look at this matrix, the rows that are empty and the columns that are empty represent new users and new movies. And collaborative filtering does not work for these people or movies. And so if we have a high proportion of new users and movies, we might consider using some content-based filtering or a hybrid of both collaborative and content-based filtering. But for the purpose of this talk, let's just assume that we have a data set that's dense enough for us to proceed. Okay, so the next step is for us to normalize our data. There will always be some overly positive users and overly negative users, so we need to account for user and item bias. I like to call these people optimists or pessimists. So for example, optimists tend to rate everything a 4 or a 5, and although a little more rare, there are some pessimists who will rate everything a 1 or a 2. And so a very simple way to account for this bias is to use mean normalization. So essentially what you do is you take the average rating of a movie and subtract that average from every user's rating of that movie. And you can do the same for the user. So you take the average rating of an average user's rating and subtract it from all of the ratings that that user gave. And so that is how we normalize our data. Okay, so now that we pre-processed our data, we now need to pick a model. And so matrix factorization is a commonly used technique in collaborative filtering. We start with our user item matrix, and we factorize it into two latent factor matrices. So we have a user factor matrix and an item factor matrix. And latent factors here are represented by K, as you can see in this diagram, and can be thought of as the latent features that underlie the interactions between users and items. So we don't actually know what each latent feature represents, but we could imagine that one feature might represent someone or a user who likes scary indie movies from the 90s. And perhaps another feature could represent someone who likes Japanese anime. But once we have these two latent factor matrices, we can reconstruct the user item matrix by taking the inner product of these two factor matrices. And this reconstructed matrix will have populated the empty cells in our original matrix. And so the population of these cells can be thought of as our predicted ratings. Okay, so there are a variety of algorithms for us to implement matrix factorization. A couple examples are alternating least squares, stochastic gradient descent, and singular value decomposition. I'm not going to go into the details of how each of these algorithms are actually implemented and the math behind it, but let's just pick alternating least squares as our model for our pipeline. Okay, so now we need to pick an evaluation metric before we start tuning our hyperparameters. So what are we trying to optimize here? A popular evaluation metric for recommendations for recommenders is precision at K, which basically looks at the top K recommendations and calculates what proportion of those recommendations were actually relevant to a user. So in this particular example, we'll be focusing on the top 10 recommendations. So of the top 10 recommendations, what proportion are relevant to the user? This is what we're going to try to optimize. Okay, so we have our model. We have an evaluation metric that we want to optimize. We can now officially start tuning our hyperparameters. But first of all, what is a hyperparameter? When I was first introduced this concept, it took me a while to fully understand. But if we think of our model as this big machine, we can see that there are little knobs on the machine where changing the configuration of them will actually affect the output of our model. So different configurations of these knobs or hyperparameters will give us different results. The issue, though, is that it's an external property of our model, so we need to try out all of these different combinations of hyperparameters and find out which ones give us the best results. So in this particular example, we're going to be tuning two hyperparameters of alternating least squares. We're going to try to tune K, which is, if you remember the matrix factorization slide that I showed, it's the number of factors or latent features of our model, and lambda, a regularization parameter. You don't really have to know what these hyperparameters represent or what they do. Just know that we're going to try all of these different combinations of them and find out which combination will give us the best result or the best precision at 10, which is our goal at this step. So there are several ways for us to do this. We can use grid search, which iterates over a set of combinations of K and lambda. So we basically run the model and evaluate it for each combination of lambda and K. Let's say we're testing out 3 different values of K and 3 different values of lambda. This means that we'll have to run our model 9 times, evaluate it 9 times, and see which of those 9 models gives us the best precision at 10. Another approach, though, is random search, which essentially just randomly selects values of lambda and k and evaluates that several times. So this might not seem very good compared to grid search, just because it's not as exhaustive, but researchers from the University of Montreal have actually shown that this approach is not only less exhaustive, but actually more effective than grid search. So scikit-learn, a popular machine learning package, has tools for these types of searches. Now, another approach to hyperparameter tuning is called sequential model-based optimization. And it's basically a smarter way of tuning your hyperparameters because it takes into consideration the results of your previous iterations when you sample hyperparameters in your current iteration. So you can consider using tools like scikit-optimize, hyperopt, or metric optimization engine, which was developed by Yelp. Now let's say that we tuned our hyperparameters and found that a k of 8 and lambda of 0.001 gave us the best precision at k. We can train our model with these optimal hyperparameters to get our predicted ratings. And we can use these results to generate our recommendations. So there's some post-processing involved, where we have to sort all of the predicted ratings and get the top N recommendations to render to the user. We may want to filter out items that a user has already interacted with. For example, if I already watched Toy Story, I don't really want to have Toy Story in my recommendations of movies to watch next. Lastly, this isn't really related to post-processing, but we can also generate item-item recommendations with our current infrastructure. So with our trained alternating least squares model, we can actually apply some similarity metrics, such as cosine similarity, to get the most similar movies of a given movie. So if you've ever seen on Netflix those recommendations that say because you watched movie X, they're basically doing item-item recommendations using some sort of similarity metric. Okay, so our last step in the pipeline is evaluation. We sort of covered this in hyperparameter tuning, but we'll talk about it in a little more detail. I first want to highlight, though, that the best way to evaluate any recommender is to test it in the wild. So if you can do some A/B testing or usability testing where you get actual feedback from real users, that is the best signal that you have a good recommender. But in many cases, that's not possible, so we're going to have to do some offline evaluation. In traditional machine learning, we split our data set in half to create a training set and a validation set. But this doesn't work for recommender models because the model won't work if you train all of your data on a separate user population than the validation set. So for recommenders, we actually mask random interactions in our matrix and use this as our training set. So we pretend that we don't know a user's rating of a movie, but we actually do, and then we can compare the predicted rating with the actual rating. And that's our way of calculating precision at 10, or any metric we want in this case. So I mentioned precision as one evaluation metric, but there are many others out there. So there's root mean squared error, recall, and also F1, which is a combination of precision and recall. But really, precision and recall are the most popular, well, from what I've seen, very popular metrics for recommender systems. They're both information retrieval metrics. And just to give you another recap of precision at K, we're basically measuring the we're measuring the proportion of relevant items in the top K recommendations. Recall, though, is slightly different. So we're looking at the proportion of items that were found in the top K recommendations. And if you look at these equations, you can see that precision is trying to minimize the number of false positives. So basically, if a recommendation made it to the top K recommendations but actually wasn't good, that is what precision at K is trying to minimize. And recall is trying to minimize the number of false negatives. So maybe there actually was a movie that was really good that didn't make it to the top recommendations. This is what recall is trying to measure. Okay, so we've looked at all of the steps involved in building a recommender pipeline. And you can modify this pipeline by choosing different models or evaluation metrics or hyperparameter tuning approaches, but really the general structure stays the same. And although these considerations are a bit outside of the scope of this presentation, I think it's really important to take into consideration interpretability, efficiency, diversity, and serendipity when we build our pipeline. So you could technically build an extremely complex neural network that gives us very precise results, but you won't be able to interpret these results, and the runtime might be very slow, so it's not very scalable for larger data sets. And lastly, there are a bunch of tools out there for you to build a recommender system of your own. I mentioned alternating least squares in my talk, and I actually use that for my own personal project using the implicit package, so it's pretty great, and I recommend you check it out. And lastly, thank you. If you have any questions about building a recommender pipeline of your own, I'm no expert by any means, but I can at least try to answer the question for you or point you in the right direction. So thank you.